So far you have looked at the Thomson plum pudding model as well as Rutherford nuclear model. Today we are going to look at the Bohr model of an atom. According to Bohr model, an, an atom resembles a miniature planetary system with electrons circulating about nucleus, and nucleus has all the concentrated positive charge at the center of an atom. It's like planet circulate sun. Now these atoms do not collapse because the attractive electrostatic Coulomb force provides the centripetal acceleration necessary to maintain the orbital motion. Now here Coulomb potential V, if you remember from your 1602 class, potential between an electron and ZE charge is given by this. And now force, Coulomb or electrostatic force between electron and nucleus is K, which is 1 over 4 pi epsilon naught, ZE square over R square. And here we have mv square over r as our centripetal force, which is necessary for electron to move in a circle of radius r at speed v, but it is electrically unstable because the electron is always accelerating towards the center of the circle. The laws of electrodynamics predict that such an accelerating charge will radiate light of frequency f equal to that of the periodic motion, which in this case is the frequency of revolution. Thus classically, let me calculate the frequency. Here small r is the radius of revolution of orbit of an electron. Now I have substituted the value of v from this equation and into here, and that gives us the frequency, and then I can further solve it and show that this value of frequency is approximately equal to 1 over r to the power 3 by 2. Now if I want to calculate the total energy of the electron, it will be a sum of kinetic and potential energies, which can be written in this format. And from previous equation we also know that half mv square, the kinetic energy, is equal to k z e square by 2r. So the total energy can now be written in another format. So now we get total energy is equal to minus k z e square over 2r, which has a dependence of minus 1 over r. Thus classical physics predicts that an energy is lost to radiation. The electron's orbit will become smaller and smaller, while the frequency of the emitted radiation will become higher and higher, further increasing the rate at which energy is lost and ending with the electron reaches the nucleus, as I showed before. Something like this. The time required for electron to spiral into the nucleus can be calculated from classical mechanics and electrodynamics together. It turns out to be less than microsecond. So at first sight, this model predicts that atom will radiate a continuous spectrum, and it will collapse into the nucleus after a very short time. A result that fortunately does not occur because we know that atoms are stable. So this collapse of electron into the nucleus does not occur. So unless excited by some external means, atoms do not radiate at all. We know that. And when excited atoms do radiate, a line spectrum is emitted, not a continuous one. Because if it is spiraling down into the nucleus, it will continuously radiate, whereas continuous radiation does not occur. A line spectrum occurs. That means atoms radiate energy only for a particular wavelength, not continuously for all wavelengths. Thus, Bohr made a daring hypothesis. According to Bohr, first of all, an electron revolving around the nucleus is not permitted in every possible orbit or radius. That means it cannot just choose any radius and revolve around the nucleus. It can move only in some special orbits in which electron may exist without radiating electromagnetic energy. It's important to note that these special orbits are called stationary states or stationary orbits. In these stationary states, the angular momentum of an electron takes values integral multiples of h bar. So L can be written as L equals to nh bar, where the lowest value of n is 1, not 0. So in stationary states, electron can have L as h bar, 2h bar, 3h bar, and so on, and not like 1.5h bar, 2.5h bar, etc. So let's say if an electron is moving around the nucleus with a radius r and linear velocity as v, then angular momentum can be written as here as shown, and this angular momentum is equal to nh bar. So I can get an equation of V, and from there I can calculate the value of kinetic energy. Earlier we have seen this value of K, kinetic energy, and here just don't get confused. 1 over 4 pi epsilon naught I have previously used as small k, and if it's an hydrogen atom, so that Z is equal to 1, this will be the kinetic energy for hydrogen atom. So if we look at this equation, now I have used a term instead of R, I'm calling it Rn. Let me make that correction on the left hand side also, because it is about a particular orbit. So we have to define that radius of a nth orbit as r with the subscript n. So we can rewrite this equation in terms of Rn, and here there are a couple of constants except n square. So I can write that as Rn equals to a naught n square. Here a naught is known as Bohr's radius. That is the minimum radii for a hydrogen atom, and here a naught is equal to 0.0529 nanometers. And if you look at this equation, then you can see that this mass is mass of an electron, E is the electronic charge, h bar, epsilon naught, pi, all are constant. So we can get this standard value. So radius of nth orbit actually depends on this Bohr radius and n square. So as we go, n can take values 1, 2, 3, 4, and that will define the radius, allowed radius for electron orbital motion. Here this formula for radius, that electrons move in a particular radius, it's important, and it's also different from what we expect from classical physics. So overall, we found that the stationary orbits of Bohr's first postulate have quantized radii, denoted by this equation. Also, it's important to note that the Bohr radius a naught for hydrogen, for which Z atomic number is 1, corresponds to the orbit radius with n equals to 1. The smallest Bohr orbit possible for an electron in an hydrogen atom, that is a naught. But if you keep the parameter Z in the kinetic energy equation, you will also see that this Bohr radius is inversely proportional to atomic number. The Bohr orbits for single electron atoms with Z greater than 1 are closer to the nucleus than the corresponding ones for hydrogen. It's important to get that information. Earlier, I have shown you that the total energy of electron is written by as this formula, but now because radii are quantized, I'm going to just use the subscript n also. And now I can substitute the value of Rn to this equation. Note that in right hand side I have not reduce this equation for hydrogen atom. That is why Z, capital Z, is still here in the formula for Rn. Thus, this is more general equation for the energy of electron in an atom. Energy equation can be solved further. It's important to note that in energy of an nth orbit is proportional to z square and is inversely proportional to n square. Here E naught is a constant which has been used for mk square e to the power 4 divided by 2h cross square. So we see, important point is we see that the energy of electron is also quantized. Now if you want to calculate this energy of n orbits for hydrogen atom, we just substitute capital Z equals to 1 and we get this value of nth energy. And here E naught is a constant equal to 13.6 electron volt. Now if I start drawing these energy levels, I get E1, which is the smallest energy or the lowest energy level for n equals to 1. So you can keep calculating the energies of different levels for different values of n. Notice that these values are for hydrogen atom, for which Z is equal to 1. So E1 here with the lowest energy state is also called the ground state, and E2, E3, E4 are corresponding excited states. For example, E2 will be first excited state for hydrogen atom, E3 will be second excited state, and so on. Another point to note is that these energy levels are not very uniformly, they don't have uniform separation between these energy levels. So this is, it does not directly depend on n, it is inversely proportional to n square. Another important point is, now electrons, let's say if it is in a particular nth orbit, then what is the binding energy of that electron in that orbit? Binding energy is the energy required to remove the electron from that orbit. So it will be equal to the magnitude of the energy of that orbit. Okay, so here binding energy is equal to magnitude of energy of that orbit. So for example, if I ask you what is the binding energy of an electron in n equals to 2 state, so here you look at for E2 it's minus 3.4 electron volt, so binding energy will be 3.4 electron volt. So if an atom absorbs energy equal to electron's binding energy, the electron can be actually removed from the atom and become a free electron. So atom minus an electron is known as an ion. Therefore, amount of energy needed to remove an electron from atom is called ionization energy. And usually this indicates energy required to remove electron from its ground state. So far we have seen Bohr's first postulate, which was that electrons could move in certain orbits without radiating. He called these orbits stationary states. Now let's look at his second postulate. Second postulate was to assume that the atoms radiate only when electron makes a transition from one stationary state to another, and that the frequency of an emitted radiation is not the frequency of motion of either stable orbit, but it's related to the energy of orbit by Planck's theory. And let's look at that formula also. Let me just show you an example what I mean by saying that when an electron makes a transition from one stationary state to another. So let's say for an atom you have a blue indicating the nucleus, and then there are two orbits shown. Let's say for n equals to 1 and n equals to 2. An electron, let's say, is in n equal to 2 state, and this electron, let's say if it transitions to a lower energy state, then it will radiate energy, or it will radiate electromagnetic radiation. The frequency of the emitted radiation can be calculated using this formula, where EI is the energy of the initial orbit and EF is the energy of the final orbit. So if the energy of the initial orbit is higher than the energy of the final orbit, then it will radiate electromagnetic radiation of frequency F, given by this formula. Here H is Planck's constant. This second assumption, which is equivalent to that of energy conservation with the emission of photon, is crucial because it deviated from classical theory, which requires the frequency of radiation to be that of the motion of the charged particle. So let's forget about that, and this will be our equation if there is any transition, equation for frequency if there is any transition taking place. So we saw that atoms don't radiate unless electron transition from one orbit to another orbit. In more general term, because we know that energies are quantized, we can write energy of Ni orbit minus energy of Nf orbit. I can continue solving this equation. Important point to note is I'm not calculating this for hydrogen only. I'm writing this general equation, and whenever you have to calculate that for hydrogen atom, simply substitute capital Z equals to 1 in these equations. So I get an equation for frequency of electromagnetic radiation. Now I can also calculate the wavelength of such radiation. Now in this equation I can substitute E naught divided by Hc as another constant, because all these are constant values. This is called Rayleigh's constant, and by substituting that in the equation for wavelength I get, and let me also give you the value of R. So now we have two formulas, one in terms of frequency, another in terms of wavelength. Remember those earlier formulas for frequency and wavelength, but let me just show you a little bit different thing about the excitation energy of an excited state N. So if you have to calculate excitation energy, it will be En of a particular state N, then it will be En minus E1. So we could calculate the first excited state for Z equals to 1, and similarly the excitation energy for the second excited state, and this is equal to -1.5 minus -13.6 equal to 12.09 electron volt. So that way you can calculate the excitation energy. So to go to higher or outer orbit, electron will need more and more energy, because as we are increasing the value of n, energies associated with those n values are increasing. So for an electron to go to a higher orbit, it needs more energy. And suppose we excite an atom by a radiation falling, then electron can actually absorb that energy and jump to a higher level. For example, let's say if electron gets some energy, electron is here and it takes the energy, it can actually jump to a higher state, and so on. We will look at those more later. Going back to the previous postulate of Bohr, we know that when an electron jumps from higher to lower energy level, it radiates electromagnetic radiation of a particular wavelength, and that wavelength or frequency depends upon the number of the orbit, like Ni and Nf. So what I'm going to do now is I will just draw energy levels for an hydrogen atom. So this is diagram of energy levels. Now we know that electron can jump from n equals to 6 to n equal to 1. It can also jump from n equals to 5 to n equal to 1, or n equals to 4 to n equal to. So I've shown you here what happens when an electron jumps from n equals to 6 to 1, 5 to 1, 4 to 1, 3 to 1, or 2 to 1. In all such cases, there is a change in energy. And if you remember, the formula of change in energy is equal to HF. So that means all these transitions will actually lead to energy radiation, and such radiation are known as Lyman series. So in Lyman series, the final transition is taking place to n equal to 1 level, and each of these correspondingly will give a line in a emission spectra. And if such transitions are happening from any of the higher energy levels to n equal to 2 state, that corresponds to Balmer series. Balmer. Similarly, if the transition is taking place from any higher excited states to n equal to 3 state, then the energy difference will lead to some special series of wavelength to be present in the emission spectra, and those series are called Paschen series. And similarly, you have other series, and I have here shown you just for hydrogen atom. And just remember that energy increases as you go higher and higher in n value. These energy levels keep on going, and as you go higher value of n, actually the energy levels are much more closely spaced. So it does not mean that E7 is not there or E8 is not there. Actually this extends up to n very large value of n, you can say up to infinite, where the energy level of, as we go higher and higher value of n, the energy of the nth orbital goes to finally 0 electron volt. So for n equals to infinity is 0. The value of energy level is 0. So bottom line, there are infinite number of levels. Their energies are given by formula En equals to minus 13.6 divided by n square electron volt. And they are so closely spaced when n is higher that I chose not to draw those, because as n is increasing, the difference between these energy levels is reducing. Here the wavelength scale in the diagram is not linear. Here I am drawing actually wavelength in a line spectra. So we have seen so far Lyman, Balmer, Paskin series. Let me also calculate how we'll show you how to calculate the wavelength for such series. So we start with what we know. We know how to calculate the wavelength if we know the initial and final values of n. So if we start with Lyman series, this you will have to remember that for Lyman series, final value of n is always 1, and initial value of n can be 2, 3, 4 or any higher. Therefore, if we substitute the value of nf square as 1, we get this formula. So now you know what is a Lyman series and how you can calculate the wavelengths in Lyman series. Similarly, for Balmer series, and similarly we can calculate for the following series, which are called bracket and P1. So with this information you can calculate wavelength and actually frequency also, because you have seen the formula for frequency for any of such series for hydrogen atom, and also if you don't substitute z equals to 1, you can calculate that for any atom. Bohr's theory can be used for any atom with a single electron even if nuclear charge is greater than 1. And for such an atom, if you don't substitute z equals to 1, we get the value of energy in terms of minus 13.6 z square over n square electron volt. And the value of radius for nth orbit will be a naught n square over z. I told you previously that it is inversely proportional to z, but probably I didn't give you the formula. So for atoms with z greater than 1, first the orbit are closer to the nucleus, and second they have large negative energies. That is, electron is more tightly bound to the nucleus. So rest of this topic we will see in the class. Please do examples in the textbook, as well as read the textbook, look at the schematic diagrams in the textbook, especially for these series of emitted radiations, Lyman, Balmer, Paskin, bracket series, and so on.